This is an overview of mathematics when you get really serious in learning mathematics and theoretical physics. To appreciate the beauty of mathematics, let's take a look at Maxwell's equation. These are the equations written as sets of partial differentiations. Now, when you learn about vector calculus, you can write this in terms of divergence and curl in simpler notation, like this. Then after you learn about differential geometry, you can write Maxwell equation in the notation of tensors, like this. And you can write it even simpler if you use exterior calculus. This is the Maxwell equation in the language of exterior calculus. The geometrical laws of physics take on a simple and elegant form in terms of exterior calculus. These are my suggestion of books. Saunders Mac write a very good book containing many modern ideas of mathematics. Saunders Mac is one of the founder of category theory. Robert Garrow also wrote a very good book, Mathematical Physics. He started the first chapter on category theory, and all the other mathematic topics is discussed from the point of view of category. There is also a book available to download on the archive by Dutaili, Mathematics for Theoretical Physics. The other book by Choke Bruha, Analysis, Manifolds and Physics, is a very comprehensive coverage of all the modern mathematics used in theoretical physics. These are the topics of mathematics that you will need to learn, starting with linear algebra, covering vector spaces, linear transformation, or matrices multiplication. So you should be able to represent any linear transformation as matrices multiplication, and should be able to determine whether the matrices are invertible, and you will also learn about eigenvectors, eigenvalues, and how to interpret the eigenvectors and eigenvalues. Then you learn about abstract algebra. So basically, the basic objects are groups. So you should be able to interpret the groups in terms of geometric symmetries, and then understand the Silo theorem about finite groups. And then you learn about rings and fields and Galois theory. You should understand the link between finite groups and finding the roots of a polynomial. So interlinking between abstract algebra and linear algebra. Then also representation theory, how to relate abstract groups to groups of matrices. Then you learn about real analysis. Basically, real analysis is calculus, but from a more formal and rigorous point of view. So usual definition of limit, continuity, differentiation, integration is discussed from a more formal point of view in terms of epsilon and deltas. So and also the convergence of functions. Then multivariable calculus. should be able to understand what does it mean to be for a factor valued function to be differentiable, and then you should be able to calculate the Jacobian of function, then also understanding the implicit function theorem. Then you learn how to calculate the divergence, curl, and gradient of a function, and also to how to do path integration along a curve. Then the important Stokes theorem. You should be able to understand Stokes theorem and why it is a generalization of the fundamental theorem of calculus. Then you learn about differential geometry, differential forms. You learn about manifolds and how to take the exterior derivative of a K-form and how to reformulate the Stokes theorem in the language of differential forms. You will also learn about curvature, how to calculate the curvature, that is the rate of change in the direction of tangent spaces, and you learn about non-Euclidean geometry, namely the hyperbolic geometry and elliptic geometry, and how the three of them are consistent with each other. Then topology, you learn about open sets. Then you can reformulate the notion of continuity from the topological point of view, like the mapping of open sets to another open sets. Also metric spaces, then topology in Rn, and the Heine-Borel theorem. Number theory is also an important subject. So you learn about axiom of choice and then countability. You should be able to show that rationals are countably infinite while real numbers are uncountably infinite. Then you learn about prime numbers, Diophantine equation, Euclidean algorithm, and you should be able to show that algebraic number field contains the analog of integers. Then you learn about complex analysis, Cauchy-Riemann equations, then Cauchy integral formula, then analytic number theory. You should know how Riemann zeta function is related to prime numbers and understanding the Riemann hypothesis. Lebesgue integration is a generalization of Riemann integration. So learn about basic ideas of Lebesgue measure, and then you should understand the Lebesgue dominating convergence theorem and the concept of sets of measure zero. Then you learn about Fourier analysis, how it is applied to a periodic function, and Fourier transform, and how it relates to Hilbert spaces. And further, how to use Fourier transform to solve some differential equations. Another important topic is differential equations. basically many problems can be reduced to differential equations, and you should be able to solve most of the differential equations to prove the existence of a solution and to formulate the initial value problem and boundary value problem. And you should also be familiar with uh, the partial differential equations, important equations including the heat equation, the wave equations, and Laplacian. In probability theory, you learn the counting rule, binomial theorem, then random variable, expected value, variance, then the link between probability and integral calculus, central limit theorem, large number theorem, and so on. And it is increasingly important to know computation and algorithm. So you should be able to understand the complexity of an algorithm, how to determine the complexity, and understanding the P, NP complexity, and also graph theory is very important nowadays. You can analyze the internet networks, social networks using graph theory. Even Google rely heavily on the graph theory to do the searching algorithm. And the application of graph theory actually is very diverse, from biology, uh, communication networks, or operation research, like scheduling of flights and so on. Numerical analysis is also important. When you cannot find the analytical solutions, you have to rely on numerical analysis to find some approximation to the solutions. An example is Newton's method for finding roots of a polynomial. Lastly, category theory. Category theory is the mathematics of mathematics. So a more general approach to different areas of mathematics. Each area of mathematics can be described by the relevant mathematical objects and the morphism between the objects. So category consists of objects and morphism between objects. And you can draw this relation with diagrams and arrows and things like that. You will also learn about functors, natural transformation, and Yoneda lemma. That's all I can say now. Thanks for watching. Bye.